Good afternoon, ladies and gentlemen. It's my pleasure and privilege to welcome you all for this distinguished lecture series, a monthly series on energy efficiency. This series, which started in the month of May 2020, has been going on for the last 2 years. We had the privilege of several industry leaders. Mr. Ravichandran Purushothaman led the first of the lectures, followed by Mr. Unnikrishnan of Thermax, Mr. Ranganath of Grundfos, Mr. V. Suresh, a doyen from the Indian building sector, Dr. Ajay Mathur, the Director General of the Energy Research Institute at that point of time, and Mr. Tejpreet Singh Chopra. These were the first 6 experts who delivered the distinguished lecture series. They were followed up by equally eminent people, Mr. Brian Madave of International Energy Agency, Dr. Naushad Forbes, the past president of CII and a known expert on energy, Dr. Jairam Varadaraj, Managing Director of LG Equipment, Padmanabhan, an international expert on energy efficiency, Dr. Rene Van Berkel, Head of Urido India, and Mr. Raghupati of CII were some of the other experts who delivered this lecture. The last 8 of them happened to be Dr. Ashok Sarkar of World Bank, Mr. Saurabh Kumar of ESL, Mr. Abhay Bakre of the Bureau of Energy Efficiency, Dr. Anshu Bharadwaj, who heads the Shakti Sustainable Energy Foundation, Mr. Chirag Baijal, the Managing Director of Carrier India, Mr. Upendra Bhatt of C Kinetics, Mr. A.R. Unnikrishnan, Managing Director of Saint Gobain, and last month we had the privilege of Mr. Vikram Kasbekar of Hero Motorcorp addressing us in the distinguished lecture series. All these lectures are available in YouTube for download as well as viewing. Today we are privileged to have the 21st distinguished lecture to be delivered by Professor Rangan Banerjee, the director of IIT Delhi. To just give you a brief background of Professor Rangan Banerjee, he took over as the director of IIT Delhi recently in February 2022. Congratulations and good wishes to you, sir, for a very, very successful tenure at IIT Delhi.
Thank you.
Professor Rangan Banerjee has been very closely associated, known for his association with IIT Bombay and energy, a very long academic education and a distinguished career at IIT Bombay. He served as the Forbes Marshall Chair Professor in the Department of Energy Science and Engineering, a department which he helped start in 2007 at IIT Bombay. He has been involved in setting up of a megawatt scale solar thermal power testing and simulation and a research facility which was supported by MNRE at IIT Bombay. His areas of interest include energy management, modeling of energy systems, energy planning, policy, hydrogen energy, and fuel cells. A man who has been, if one looks for people from the academics in energy, one of the first few names to come up is that of Professor Rangan Banerjee. His leadership and contribution has been equally outstanding. He currently serves on the editorial board of International Journal of Sustainable Energy, International Journal of Sustainable Engineering, International Journal of Thermodynamic Solar Energy Advances, Global Transitions and Energy Transitions. He has been advising several city, state regulatory commissions and energy agencies, Planning Commission, Niti Aayog, MNRE and energy-related issues. He was earlier the Dean R&D of at IIT Bombay and has received the Excellence in Teaching Award from IIT Bombay. He is also an adjunct facility in the Department of Engineering and Public Policy at Carnegie Mellon University. We are privileged to have you, Professor Rangan Banerjee, to deliver this lecture today. Is being seen by mostly, sir, industry participants from all over the country. This is also, apart from the WebEx platform, this is also being relayed on YouTube and Facebook. And many of the places in the industry, sir, like we have here, the CIIs, all the staff, about 30-35, sitting in one place and listening to a lecture. In many of the other places, the employees assemble at one common place, and the lecture is being, relayed on a huge screen for all of them to see. Without much further ado, it's my pleasure and privilege once again to welcome you, Professor Rangan Banerjee, and over to you, sir, for your lecture. Thank you.
Thank you, and it's a proud privilege, and I'm delighted to be here talking to all experts who are people in the energy efficiency space. And I noticed that I'm the 21st speaker in this, and I think probably the first academic. So I was just looking at the names. I think energy efficiency is more about actually doing things on the ground. And I think a lot of expertise, basically, whether it is technology, whether it is systems, whether it is policies, and you have people who are thinkers, people who've had things. But as an academic, I would like to, so I am going to, I guess, talk to you for about half an hour. Is that correct? Half an hour is the time?
Perfect, sir.
Yeah. So you can just give me a sort of, when I'm nearing the time, you can just tell me so that I can wind up a few minutes before, and then we can take some time to take questions. So I'll share I hope you can see the slides. You just confirm once that you can see the slides. Is that visible?
Yeah, we can see the slides, sir. We can see the slides. Thank you.
Okay, excellent. So what I'm going to do is I'm going to take you through, I'm going to give you a perspective on energy efficiency. So I'll start off initially by looking at defining efficiency, and then talking about a little bit of a historical perspective, and then give you some examples and talk also about, how we can look at modeling, and we will take some examples from industry and buildings. And then towards the end, I would like to define how is this going to change in the future and what is the focus. So I'll leave you with a couple of thoughts towards the end. So I'm going to talk to you a little bit about, start with defining efficiency, give you some examples of things which our students have done and some of the research things, and then try to give a perspective of what does it mean in the future, how is it going to be different. So as we all know, energy efficiency is defined as typically the energy output divided by the energy input. And mostly we always talk about this from the first law. And the basis is the output defined based on the purpose of the device. If you're talking of a power plant, it's the electricity output. If it's a boiler, it's the heat and the steam which you're generating. And then we also know that there is the second law of thermodynamics, which of course came first, but because it's so difficult to apply, people usually look at, in the second law, we talk about an exergy output, or the available energy by the exergy input. And there are certain things which one can think of when one looks at the second law. We'll talk a little bit about that also. So just to give you, this was one of the first practical examples. This is way back. We are talking of the steam engine and the first efficiency measurements. Okay. And this is essentially, we are talking of something like 1800s. This is a paper where and we'll give you the reference to it. It's there in the, you will see where you're looking at the water which is being, the engine and how much water is being expelled. We are looking at the total output which is coming out, and this was used to define an efficiency and to compare different kinds of designs. We also had an energy service company. The first concept of the energy service company was actually way back by James Watt. Okay, James Watt was a very nice innovator, but he was also a very good businessman. So he started off by saying, we will leave us. This was a time when he was, you were competing against horses, because earlier it was horsepower which we are talking of. So he says, we will leave a steam engine free of charge to you. We will install these and take over the operation for 5 years, customer services. We will guarantee you that the coal for the machine costs less than you spend as fodder on the horses which do the same amount of work. And we are talking of lifting certain things. You're thinking of lifting water, and everything that we require of you, you give us a third of the money which you save. And it's very interesting. And then he had also certain patents, and then they had this Watt and Bolton. So just to show you that the energy service concept, ESCO concept, is also not really new. It started off initially as. Now this is some of the things which you may want to think about, and something which I'm sure all of you have slogans, and you've said, if you talk about whether an unit of energy saved is equal to a unit of energy generated, or is a unit of energy saved more than a unit of energy generated, or less than a unit of energy generated. Now, most of the energy professionals on this platform will say that it is usually more than a unit of energy generated, and I'll explain why. And then this is something that all of us have seen. Basically, whenever we talk about energy, today what you're seeing is in your rooms which are air conditioned, or in the display that we are seeing, there is finally an illumination, there's a comfort, there is a final end use that we are looking at, the end use activity. But in order to have that end use activity, we are using the energy that is available in nature. That primary energy earlier used to be mainly fossil, coal, oil, natural gas, and now we are talking of solar, we are talking of wind. This primary energy in the form that it's available in nature is not really directly useful to us. So it goes through a sequence of conversion steps. So instead of coal, you mine it, you wash it, you put it into a power plant facility, you generate electricity, you have the secondary energy. That secondary energy goes through a transmission and distribution system. You have the final energy that you buy in your CII center. If you're buying it from some discom, you then use it within your building to run your air conditioning system, or you use it for your compressed air, or you use it, so you get the useful energy which gives you the end use service. Now, to get each of these conversion steps that we have, some part of the energy that we are taking is used up, because these are all finite, these are all actual processes, so there will be irreversibilities, there will be losses. So when we need 1 unit of useful energy, depending on the system, we may need 2 units or 3 units of primary energy. So naturally what we say is 1 unit of energy saved is usually much more than 1 unit of energy generated. So this is one of the things that we need to keep in mind, and we need to look at the entire chain. And I'm sure this is something most of you are familiar with. Now, this is another question which I think energy professionals all have a straight answer to it. We say, yes, of course it results in energy savings, but economists have a different opinion on it. So the question is, does energy efficiency always result in energy savings? Okay. And in order to look at that, again, just think of a thought exercise. Suppose you use a car and you drive 3,000 kilometers annually in a car, which gives you an average fuel economy of, let's say, 15 kilometers per liter with a particular constant price of petrol. Now now it's talking of 90 or 100 rupees per liter. You can find out, you can say annually, this is how much I'll spend. If your car is made more efficient with some retrofit, so the fuel economy is now 20 kilometers per liter, how much would you save? The simple engineering way of calculating this is we just calculate so many kilometers divided by the amount of kilometers per liter, you get so many liters, multiply that by the price, and you get the annual amount of energy that we would, energy and cost, and then we can get, when we have 20 kilometers per liter, we'll have relatively less, and accordingly we get, this is the amount of cost saving. But actually, if you see, and this is something you see in many of the vehicle ads, you see that this is so efficient that you take more, you drive more, because you know that I have a more efficient car, right? So this is basically what is, in a simple way, this is what is called the rebound effect. And in the most extreme case, if the rebound is so much, it might actually backfire where you use more energy and there are, of course, examples of this, but the answer for energy efficiency professionals is, in general, the rebound effect is relatively small. Again, very little studies in the Indian context. And again, in this case also, there is a historical case. So way back in 1866, William Jevons had said it is wholly a confusion of ideas to suppose that the economical use of fuel is equivalent to a diminished consumption. The very contrary is the truth. And he basically said that the more we start making coal efficient, the more users you get for coal, and so the consumption of coal at the national level actually starts increasing, and that's actually what happened. So this is the kind of rebound, and this is from, you can see the paper, so he talks about coal being used in the blast furnace, but then you start having more and more steel and pig iron being used, so that becomes more. So this is the kind of thing, and there's an interesting article in the New Yorker, which is called the Jevons paradox, and which basically says that You can see that on your cell phone. You see, cell phones we have made them more efficient, and then you have more and more, but then you start using more things from the cell phone. So the overall battery size and the energy consumption, even though the thing is more efficient, over a period of time, you start getting more usage. So this is the kind of paradox. But typically, globally, these are the kind of rebound effects are usually small. All less than 100%, all basically 10 to 20%. And so we do have energy efficiency. And this is something where we need to have more studies on direct rebound, indirect economy, and we can calculate this. So this was one classic example of a rebound. In UK, there was a chain of, this is an old example, well documented. A supermarket chain actually provided an incentive that if you bought, instead of incandescents, you bought compact fluorescents, you would get air miles. And it turned out that the number of air miles, if you did the calculations, it was actually CO2, you are increasing your total CO2 impact. But this is just to show you some of the things which are there. So these are direct, indirect. Let me just, okay. Now the other thing which you may want to see is if you look at, let's say, one of the things driving our total energy sector and energy efficiency is basically this whole issue of climate change. And as you know, our Prime Minister in Glasgow has made a commitment by 2070, we are going to go to net zero. Now, if you look at a particular year and you start saying that, okay, as compared to 2020, we want to go to 2030 and see total amount of CO2 reduction that we want to have, annual reduction, and then see all the options which are there and then rate them with a marginal abatement curve. So basically on the y-axis, what we have is the cost per ton of CO2. And on the x-axis is the million tons of CO2 that we are saving. You will find typically that this is one of the McKinsey curves which was done for India, and you can see that on the. You will find that there are a number of things for which the cost of abatement is negative, and the reason for that is they are anyway cost effective, and almost all of those are energy efficiency. So actually, energy efficiency makes a lot of business sense, even if you don't count the carbon. And of course, there are reasons why there are barriers and things and the way in which you look at this. So it just makes sense in that. So whenever we talk about this, so let me now take you through a few examples. And the classical way to do this is to do an energy audit of an industry. This term got coined after the oil shocks in the 1970s. And typically, you can go through a structured way of doing an audit, identify, measure, look at doing mass and energy balances, list out all your energy conservation opportunities, prioritize them in terms of their cost-benefit ratios, and then we can then go ahead and install the measures, do a post-audit and see. So typically what happens is we have many types of energy conservation opportunities, and of course, most of these opportunities are more at the design stage, where we can do an efficient process design, we can look at efficient equipment design and selection, we can design the utility system for the process, and then once you have it, then we can do an energy audit, we can change the operating strategies, we can retrofit the equipment. For instance, something is there where the flue gases are going out, I can put a waste heat recovery device, or I have, let's say, I have a pump which is operating at, you're throttling it and controlling it, you can put a variable speed drive. These are all standard things. And then if your equipment or process is inefficient, we can actually replace it. So that's the other. So when you do an audit, now this was one, it's an old paper, but it's an actual audit of a cement factory in UP where you can see when this is a Sankey or an energy balance diagram, you can see in the cement that there is already some inbuilt loops where we are recovering some of the energy in different sectors. In all these cases, what we do often is we do benchmarking, and I think with the PAT, which is now prevalent in our country, we are monitoring the specific energy consumption. So typically, what happens is we take the entire set of, let's say, cement plants or steel plants or aluminum plants, and we can then see that what is the specific energy consumption vis-a-vis, and we arrange them from the most efficient to the least efficient, and then we put the top 10%, and that becomes sort of a best practice plant, or that's the target, and then we can see. So in the Indian context, for most of the places, we see that we have a lot of very efficient plants competing with plants which are actually at the tail end, and so this is one of the things. The other thing which has happened is we have now a standard which is a voluntary international standard for monitoring and looking at energy management within an industrial context. When we talk about industrial context, we are basically, every industry starts with raw materials and creates products, and in the process we are using the utilities, and we want to see that can we minimize the use of these utilities so that we use the things internally, and this is where we can use pinch and process integration, and so that we minimize the amount of waste, minimize the amount of utility, and this is a very well-defined area where there is a lot of research. There are lots of commercial organizations also in this space, and this is something that can be. Now the question is, often all of us in the energy efficiency domain often feel that we are already done. We benchmark ourselves with others, and we say we are the best in the, let's say we are the best plant in the country, and maybe even the best in the world. So the question is, are we reaching our limits to energy efficiency? And to do this is something I was involved in the global energy assessment. This actually came out in 2012. You can see this. It's a book by the Cambridge University Press, but you can see chapter 8. It's available online. It's freely available. The chapter is freely available. And you will see we did this, Mark Rosen of Canada did this for us. And what we did is we took all the entire world's industrial process and we tried to do a first law and second law efficiency. And we found that the second law efficiency of the industrial sector is just 30%, while the first law is about 50%, which means that many of our processes actually can be revamped so that they become much more efficient thermodynamically. Is this going to happen automatically? No, it won't happen automatically, because all the competing industries, there are significant investments required to make that. But technically, it is very much possible to do a lot of, to make these modifications. The other thing that we did, and this is one of our PhD students who had done this work, we created a process where you see, when you create a model, you talk about it theoretically. But when you look at the other end, is you do an audit and you see what is happening in the industry. We coupled these. We said, okay, let us look at any industry which exists and let's create a model which is for that particular set of equipments with that process. And we develop this hands-on. We then build up a set of models, mass and energy and flows, and then we validate that model with the data. And then we use that model to see what ifs and how we can change parameters in that industrial context to actually reduce the energy consumption. So we did this for the glass furnace, and the glass is the process of making glass is actually very energy intensive industry. We looked at the airflows, we looked at the stoichiometry of the fuel, the glass reaction, furnace geometry, and then the regenerator combustion zone, and then there was a loop. This was a set of models, and then we validated it with a number of glass furnaces and took data from these sensors, temperature, composition, etc., validated the model. Then we built we built a tool which you could use to get the specific energy consumption and the Sankey diagram and the different losses. And then we had an ideal and an actual, and we had a workshop with about a set of glass industries. Each one put their own data, and then we saw, you can see the bars where the lower value is the model, the ideal, what can be achieved with that plant and what was actually there, and it shows this. So this was a scheme for model-based benchmarking. We also did this for mining, and this was where dump trucks and excavators. We also looked at, this is a mine transport model. We did mine water and energy management in assessment in mines. again created a model. And so I think what I wanted to say is it is possible to look at the existing structure and the process and look at creating models and then see how we can do model-based benchmarking to go beyond what exists today. And this is one step beyond the audit, but it is not going to the process modification, and process modification at the design stage also you can do. The other thing that we want to see, and this is, I'll come back to this at the end, where we talk about actually in many of the industrial processes, we can reform the process to actually make it a zero carbon process. So even a process which is high temperature carbothermal reduction of zinc production, which is can be done with solar carbothermal. So this is basically, there's a 300 kilowatt solar chemical plant, and we used this data and created an assessment by which we can look at a fully functional method by doing solar and using a zero carbon zinc production. Again, this is currently high cost, but it is something that can be done. Similar kinds of things you can look at steel, cement, and then these are sort of, this is just to illustrate to you that we are nowhere near the bounds of where we are going. Now, let me give you some examples in buildings, and this is this is a student team, enthusiastic set of people who built a fully functional solar house, 5 kilowatt of PV on top, some solar thermal on top, insulation, and we built this house in Versailles in France. We were the first team to compete in the Solar Decathlon Europe. We rebuilt this house on the IIT Bombay campus, and this was typically, these are some of the images from that building, and this is the way it's insulated. So typically what happened is we simulated and reduced the energy footprint of the building, and then we put PV on top to do this. We did building simulations. We also looked at the kind of views and the illumination, and you can see on this the initial base case, and then with adaptive control and ventilation, with double glazed windows, overhangs, insulation, and energy efficient AC, we significantly reduced the kilowatt hour per meter squared per year. And then we build on the top, and we put PV, and actually during the days of the competition, on the actual performance of the building, this one was, we actually got the highest net energy supplied, and that was because we had done a single axis tracking which we had optimized for that location in France. So you can see this is the actual performance of building input energy and the building output energy. So anyway, these slides I will share with you. We also, another PhD student who had worked on basically where we looked at, when we design a building and you simulate a building, there are a large number of parameters that we choose. And so what we thought is we can use some method from the theory of experiments to reduce that and create a simple modified model for the building so that you don't have to simulate the entire building, and we can use that to create an optimization so that we can either minimize the cost or improve the energy performance. And this is what we try to do with a series of, you can see this window to wall ratio and the overhang depth. There were a whole host of choices for a 3-story building. And then we developed some correlations, and then we optimized it and got the final thing. Another thing which will be useful in buildings is the use of phase change materials. We had done a small exercise where we looked at phase change materials with buildings and saw the impact of that on the built environment, so that the air conditioning temperatures, actually the requirement for AC reduced. We also have been doing mixed mode studies. So there was a PhD student who just finished where we look at ceiling fan integrated air conditioning, and then the set point can change, and then the control can be done. And we also looked at predictive modeling for this. So we tried this out again in that Team Shunya house. Of course, you can see that you have wires and other controllers which have been put over here. But basically what happens in this is we have done a real-time simulation with hardware in the loop, and where we are looking at external air temperature, we're looking at the PV, and we're looking at this. And so this is again something where we have comfort-driven model predictive control based on this. And we saw that we can get, we could get significant amount of about 18% saving as compared to the normal air conditioning. And again, the airflow and then this. So now, just to now come back to the last few things which I wanted to talk about. The question is, does the energy efficiency metric remain relevant? And what is the reason for asking for that? See, the initial energy system which we were talking of is for coal, oil, natural gas. All of these were stocks. And now what we are talking of is we have converted that into flows. So we are talking of solar energy, wind. Now that energy source itself is not too much constrained. So that is not a critical source in that sense. The scarcity of that is not much. There is a scarcity in terms of the capital cost, and you're looking at PV modules and other things. So the cost may become a metric. The other metrics which will be important are sustainability related metrics, which are water, emissions, land, and the cost. As I said, renewable energy may not, the source itself may not be constrained. We may also want to look at all the materials that we are using and look at embodied energy, embodied carbon. We may look at the entire life cycle, and that should be energy payback period. Not just the payback period of the cost, but also the energy payback period. And then there may be additional indices. I could indicate some of those. So just to give you some glimpses from papers, this is where, from Allwood, this is a paper where we are looking at material efficiency. We can actually redesign our equipments and processes so that we dematerialize, we use less materials. And then the materials that we use also, we use less energy intensive materials, less carbon intensive materials, and then go ahead. So we are talking of different product design, different kinds of materials, and so on. So this is, Ashby had prepared a set of charts, which is very interesting. And I think you can prepare a whole set of different, when we choose materials, and you can see for a particular performance, in this case, suppose Young's modulus is the performance that you want, you can see on the x-axis is the embodied energy per meter cube and the performance which you want, and you have different kinds of polymers, metals, etc., ceramics. You can choose based on the embodied energy. You can also do the same thing based on embodied carbon. And there are many more papers. I don't want to get into details of this, but this is just to illustrate to you the strength and embodied energy. So you can actually have a systematic way of decarbonizing your product or reducing the energy impact of your product. And this is again something which we may want to think about. So I am going to now this is sort of my last slide, and I'll spend a little bit of time on this and then open it up for questions. So the first thing is, we must do benchmarking, and we must also look at sharing best practices. So I think in industry, we do compete, but in addition to competition, we must also collaborate, because often even the segment that you are in, that if we look at the best practices, then you may actually survive in the market for a longer period. Another issue which is very clearly understood now is that often there's no level playing field for efficiency, and the savings that we get come out of some other. This is very classically true for many of our like for instance the government, or with, let's say, an IIT or a public sector. Often you have different budgets, and the capital budget and the operating budget are different. There are also a lot of co-benefits, and sometimes what happens is, because we do efficiency, we are able to improve the throughput, and that might make more of an economic case than the efficiency itself. One of the things which we have not looked at to the extent we should is dematerialization and redesign of products. And you will see in Germany and in many of these Scandinavian and European countries, this whole eco-design concept. We can redesign the product. As things go, as we change the nature of our energy system, and we're going to have more renewable storage, timing and demand response are going to be important. So in efficiency, we also need to see when we need and what are the things. Most of our energy systems are still continuing to be large scale. And even when we go, for renewables, we are going into this level where we have 640 megawatts of solar PV. We are talking of gigawatt level plants. But there is also a trend where the Internet of Things and the sensors, the costs have come down. We can think in terms of Internet of Things, modeling, AI, ML, where decentralized control and looking at ways in which we can see how we can do predictive predictive maintenance, we can do energy efficient part load operation, we can do a whole host of things. And this is something which we can look at smart manufacturing. And this is, of course, in IIT Delhi, we have a center of excellence in smart manufacturing, and some of these throughputs and the things you may want to come and visit and see, there are things that we could do there. From best practices, we need to look at next practices, and the next practices, we have to look at low carbon decarbonization of our industry. We need to think in terms of, in many of these cases, when we look at process changes and technologies, this needs long-term R&D, we need consortium approaches. We need to also have some grand challenges, again, from between industry and academia on innovations. We need to think in terms of prototypes and demonstrations. Now, we have today the ability to create designer materials, right? We have nanotechnology, we have bio-inspired materials. And this opens up again a completely new world, because we can do materials in the way we want, we can do phase change, we can do storage. And of course, these are more longer term things, but in future, this is something, future industrial growth can be zero carbon growth. And that is something which we can use. Many industrial groups have been talking about this. And this is something which would be. So in a sense, I'm saying that it's not just about efficiency now. We also need to look at the environment. We need to look at we need to look at decarbonizing. We need to look at reducing the environmental impact, and we need to look at sustainability. But all the things that we've learned in the journey which we've done on efficiency can be tailor-made and modified a little bit, and we can go forward. And this is something where there's a benefit to the company, because it can improve our competitiveness, it can improve our market share, and we can also be seen to be, socially doing the right thing and actually making a commitment to the overall goal of zero carbon, and of committing to the governments and the societal need that is there. So with this, these are some of the references. I'd like to thank some of the people whose inputs I've used in this presentation. Thank you. I'll be happy to try to answer any questions that people may have. With this, I think I'm sort of at the end of my time. Thank you.
Thanks a lot, Professor Banerjee. Thank you so much for your address. I think you covered, from the definition of efficiency to the rebound effect to the energy conservation opportunities. Also questioned the limits on energy efficiency, spoke about benchmarking, modeling, mapping, but I think you beautifully summarized on the strategies here. You looked at 8 key strategies as far as the next steps are concerned. There are quite a few questions which have come up, Professor Banerjee. I'll try to kind of group them together and pose them to you to seek your responses. The first question was on the rebound effect that you spoke about. Similar to the examples that you spoke about, Professor Banerjee, the question is, with the increased generation of energy from renewables, and do you see the cost coming down, and do you also see a scenario where the energy consumption might actually increase over a period of time because of more renewables coming into the energy mix? Any views on that?
Yeah, so I think the energy, when we come up with, with the energy system, it's not just the cost. If you're talking of electricity, it's an overall system cost that we are talking of. So if you look at it, we have not really seen the energy costs coming down significantly. So though, at the cost of generation now, because we've been very successful in our solar policies in terms of being able to pull down the costs by lumping and making targets, and by incentivizing people to participate. And with the result that now we have, generation tariffs in the order of 2 rupees or 2 rupees 30 or of that per kilowatt hour. However, what happens is that when you see these and you see a larger penetration of renewables, we get to a situation where any additional amount that we are going to get through solar has to go through storage to be used in the evenings or the night, which means as of today's prices, that adds at least 4 to 5 rupees per kilowatt hour. So these cost things, I hope we would see a situation where renewables will result in an average cost of energy coming down, but the evidence does not show that yet, right? The evidence shows very significant learning cost effects in terms of technology of supply, but when we look at the supply and the transmission and distribution and then this thing, and then there is the issue of we have already made these investments in these coal plants and these things, and they become stranded assets and we have to pay for it. So that's one thing. But yes, if the energy really did become cheaper, then we could see the consumption going up, even though, and this is some of the things in which you see when we go forward and you look at efficiency improving, and then still so we have to see how that works out, how that dynamics works out. And I think some of these things will depend on how things play out. I mean, people are talking about hydrogen, but very clearly storage is an issue, right? And another thing that is an issue is going to be, if you look at decarbonization, we need to look at cooking, because right now our solution for cooking is LPG. And if LPG goes off, then that is the thing. So in terms of the price and quantity study and the rebound, you are right. The questioner is right in thinking that yes, if energy becomes relatively cheaper, we may and it's all going to be renewables. But I think that is I think it's still early days to see that kind of optimism. I see problems because, in the ground reality is that discoms have a lot of accumulated debt. And then we are actually so we're going to struggle in this, stumble through in a sense.
Thank you, Professor. The second question was on the metrics that you spoke about in terms of how we look at energy efficiency. And the question was, is energy productivity approach a better way to look at it in terms of the value addition for the energy input that is coming in? Is that an approach that you suggest industry should look at for energy efficiency gains?
So energy productivity as an approach is a good approach, provided the energy is scarce and if the renewable energy is short. So I think typically what we do is, I have proposed that we look at, there is this energy return on investment which is considered, or the energy payback. These are typically to be calculated for new energy sources where the markets are still not well defined. Otherwise, the ideal thing is to see, or in places where, a lot of, in the energy sector, there is a lot of interventions and it's not really completely market. So the prices happen, the sort of fluctuations which are outside your control. So I am just suggesting that the energy productivity in terms of, I don't know whether you are talking of energy productivity per unit, then you convert it into money terms. So, but there are issues related to this. But I think it is good to calculate physically how much is the overall over the life cycle, how much energy we are consuming and how much energy we are getting. And if we benchmark it against something which we have, that can be an additional metric. So I think in all these, our decision making is based on multiple metrics, and taking one metric on its own may not be appropriate. And that is why I said other factors, looking at the carbon footprint, looking at sustainability, and looking at the energy metric may be relevant. This is particularly true for new energy sources where the market is not developed.
Thank you. Professor, you also spoke about limits of energy efficiency. I mean, if you look at some of our sectors in India, the cement plants, the refineries, some fertilizer units, they are the most efficient globally. They have some of the best technologies implemented, the latest ones already in place. But the question that comes is, most or all of these technologies are imported technologies. the Indian industry has been extremely good in implementing technologies, but not so good in developing newer technologies. Is there something that you think institutes and industry together can do something about it in terms of getting the best of technologies indigenously developed and implemented?
Yes, I think this is something that definitely is something which we should do. Today itself, by chance, we were having a discussion with a group from CII, Mr. Vipin Sondi, who's leading, I think, your technology innovation things, and we were discussing exactly this issue. The point is this. The technology development, so the first thing is that though our fertilizers are actually benchmarked with some of the best in the world, similarly you will see that for some of our cement factories, it doesn't mean that even the best of whatever is the best performance of the plant, the best in the world, is not still at the limit. There are possibilities to have technology improvements where we can go beyond that. The second part of it is we are used to actually taking the best technologies, whatever is commercially available. Now, the question is, in terms of our strategic advantage, can we build new technologies? Now, that is not going to come to you tomorrow. So we'll need to take a longer time frame, but we need to then think through with the industry and the academia and make a plan in some key areas where we will have a strategic competitive advantage in doing that. So I think absolutely we must do that. We've not been very successful except a few exceptions on this, but we've not tried also in that way. And I think it is very important because that is, that's the core of being Atmanirbhar. That's also the core in which we can get, where we finally will have to compete globally, right? So I think there is definitely a niche. We need to sit together and identify a few areas where we can do this. Yeah, absolutely. And we've, as an institutional head at IIT Delhi, if you are, if some industry wants to do this and we would like to, we'll be happy to work with you on that journey.
Thank you, sir. Sir, you spoke about energy service companies or ESCOs and related it to James Watt. I mean, it's been as old as James Watt was. And if you look back at where we are in India, it looks like it's still not a successful endeavor yet. I mean, we still don't have many successful ESCOs implementing large number of projects. The potential is much, much larger than what is happening on the ground today. Any thoughts on what could be done on the ESCO markets? How do we get a more vibrant ESCO market?
Actually, I looked at this, and internationally, if you see, most of the ESCOs have been more active in the commercial and building spaces, commercial and residential. Our ESCOs, because of the way in which the tariffs and the consumption is there, our ESCOs try to focus on the industrial segment. Our industrial segment is extremely cost conscious. And the whole ESCO model actually works on taking a very large proportion of the shared savings. There are also some issues related to the, there is this thing where, your production may change. And so you have to have, again, the agreements have to be. So performance contracting is something which has worked, but there are certain reasons in which the ESCOs and also many of our industries on their energy efficiency and others, we have sufficient, we understand internally, we have enough capability to understand. So it's been difficult to, so I don't have a clear, but if as we go for these larger and larger commercial buildings and complexes, I think there is a role for ESCOs in that space. In industries, they would have to be very specific, and typically what happens is people ask you, even for energy audits, they ask you, how many paper plants have you, how many plants they want that domain expertise, only then the people will give you confidence. So I think, so I know that ESCOs, barring a few exceptions, haven't been that successful. But it's a tricky, it's a tricky question. These were just some of the thoughts I had.
Thank you. Professor, you spoke about decarbonization and net zero. What are your views on how is India poised towards achieving it? What do you think are the key levers that we should look at, particularly focusing on energy efficiency or clean technologies? How do you think one should approach towards becoming net zero or decarbonized? Decarbonizing the economy?
So I think the first thing which we should think of is we should track, again, depending on in our industry or our product or our business, we should look at our carbon footprint, and we should have a mechanism to track that, and we should have a plan of how it is going to go down. We are doing a similar kind of exercise at IIT Delhi, and we are making a plan to go net zero in some point. We have a group of people working on that. In the Indian context, the easiest thing is going to be relatively easier thing is going to be decarbonization of the electricity sector, and we are going in that direction. The challenge is going to be actually, and this is where the government is actually batting for hydrogen, but hydrogen is still not, we have to wait and see what happens, but that's one of the possible things which is there. One possibility will be where you replace fuels with electrification. Share of electricity can go up. Biomass could be a part of the solution, modern biomass techniques, but again, biomass availability, and there are questions on many of these things. So, but this is something where I think every industry or business must track and make a plan. And I think the design stage itself, in the case of buildings, I think one of the things is whenever we have a building, before we build it, we must estimate what will its performance be like. And then we can look at the kind of materials we are using. I think your GBC does a lot of work, and you also have, I think many of these, there are things which we can do. So it's an overall goal, and I think we'll be aware of it and move step by step towards it. And so I think efficiency definitely is a no-brainer for it, because that reduces things, but efficiency by itself will not be enough.
Thank you, sir. So the next question is on the startups. I mean, we are right now at a time where there are a large number of startups coming up in India. The environment is conducive. We see a large number of startups coming in, but roughly less than 5% of them are in the clean technology space or in the spaces of interest for this topic. I mean, is there anything that you think we should do in terms of increasing more number of startups in this domain, sir? Because the number of challenges that are there to solve are much more. Any thoughts on how do we accelerate more number of startups in the clean tech space?
I think we should have. So there was earlier, I don't know what is the status of it. I was one of their advisors at IIM Ahmedabad. There was a business incubator which was focusing on clean energy. It was called Infuse. And I think with CII, if you are interested, at IIT Delhi, we have a very strong startup support culture, and we want to actually accelerate that. So if there is something you think we can do together in this, and there's some kind of, one is, you have some risk guarantees, you can provide some incentives, you can have mentors, and so there are many things that we can do in this domain. And in different parts of it, many people are in the monitoring, some people are in the controls, and I think industry can definitely play a role. They're happy to try and see offline to look at areas in which we can do something in the clean energy area. Now in the electric vehicle and the EV charging and other things, there are quite a few startups coming in. And we have a few in our campus itself also at IIT Delhi. Yeah, but there is, I think I agree with you that we need to have more, and we could incentivize, we could provide training, provide funds, and do that. Yeah.
Thank you. So this question is quite broad in terms of to take your thoughts or take your opinion on what kind of technology trends are we seeing coming up in near future, sir? I mean, you spoke about hydrogen. There is also a whole lot of discussion that is happening on carbon capture and storage, carbon capture and utilization, on artificial intelligence, on industry 4.0. So what kind of technology trends do you see happening, sir, in the next maybe 5 to 10 years? What could be the big game changer technologies that could come in?
That's a difficult question. One of the things which is happening very clearly is we are clearly seeing a lot of Internet of Things and sensors and artificial intelligence and machine learning. It is happening in almost all domains, and I think it's happening in the building space. It's also happening in the industry control space. Some of this is often done by people who don't have domain knowledge. And I think coupling domain knowledge with, you have what we call as gray box models. So you have something and then you use AI, ML. So real-time kind of control and distributed control. There's a lot of scope in that. I think that we are definitely seeing. On the material side, I think there are lots of interesting things because we are now able to modify material properties and do that. So I think that's the second strand which is going to be interesting. So processes also, and the way we do processing, that can also change with this 3D printing and so we need to be nimble and flexible. And many of these things, some of them, of course, when they come, they are hype, but we have to see for ourselves what it will mean for our industry and our segment. And also there are, depending on materials and the competitive materials, many industries, the reality will change. So we need to be able to see these signals and look at it. And we may want to then see which domains we want to do technology development or R&D in. And from the energy efficiency point of view, I think the important thing to focus is to look at efficiency and renewables together, and to look at different segments in that. And I think there's a lot of things to be done. And there what happens is, because of timing, the control, and again the demand response and storage and phase change materials, lot of scope. Some things have been thought of, but some things have not. And I also feel that some of the transitions which are there for climate, we are already seeing some effects of global warming. We are doing mitigation, but there will also have to be adaptation. And some things, some industries, for instance, we're looking at coal. What do we do with coal? What do we do with the different, and how do we rework? So lots of things to be done. The rules of the game are changing, and we need to think through and work with this. And this is, I think, where academia can work with industry to provide leadership of thought. Otherwise, we will be only reacting. We have to be a little proactive in this. I'm not sure if that answers, but it's a sort of generic answer. Yeah.
Thank you. Thank you so much, Professor Banerjee, for your time. We're just about the end of the time that we have sought from you for today's session. Thank you so much for joining us. Thank you for your address, and thank you for patiently answering all the questions that have come. There are, of course, several other questions in terms of LCA, in terms of hydrogen, in EVs. Many other questions have come, but in the interest of time, thank you so much for joining us. Thanks for your session today. I leave the floor open to you for your closing remarks, sir, and with that, we could close today's session, please. Over to you, sir.
You want me to say something at the end?
Yes, sir.
Okay. So thank you. I hope, I think this is for industry and academia to work together. The energy efficiency, renewables, the energy space is actually a very challenging space today. It's a challenge as well as an opportunity. And if we want to capture it properly, I think we can actually work together, articulate what we can do, and then we can use this to get a strategic competitive advantage. And I'm grateful to CII for giving me this opportunity to talk to you, and I hope some of you will follow up and we can actually do something together, and something which will be mutually beneficial. Thank you.